Power transformers are the static, billion-dollar workhorses of the global electrical grid. But despite their massive steel construction, they can be permanently destroyed in seconds by microscopic internal failures. Traditionally, protecting these assets means monitoring their electrical current. Relays constantly measure the amps flowing into and out of the system to ensure operating limits aren't breached. But this purely electrical approach creates a massive blind spot. Because these relays only trip when current spikes, they are entirely blind to slow, low-magnitude degradation happening deep inside the insulation. If engineers wait for an internal short circuit to grow large enough to finally register on an external current monitor, it's too late. The damage is already catastrophic and uncontainable. To prevent this, engineers rely on a dual-layered protection architecture. They monitor both the electrical current and the internal chemistry of the transformer. Looking at the sheer scale of this vintage transformer tank, you can see the vast volume of dielectric oil inside. The first layer of defense involves identifying the physical and chemical symptoms of degradation within that oil pool, long before any electrical thresholds are crossed. The second layer involves calculating precise electrical overcurrent thresholds. This ensures the unit can instantly isolate itself from massive external short circuits on the wider power network. True grid survivability depends on bringing these two systems together. It requires bridging the gap between mechanical, gas-actuated devices and mathematical relay logic. Inside that massive tank, the transformer's core and copper windings are entirely submerged in thousands of gallons of dielectric oil. This animated diagram shows a cross-section of paper-insulated copper windings. When a localized internal fault occurs, it creates an intense, glowing hotspot. That extreme heat chemically breaks down the oil and solid paper insulation. This produces diagnostic gases, like hydrogen and ethylene, forming small bubbles. Because these gases are significantly lighter than the cooling oil, simple physics takes over. The bubbles naturally travel upward, flowing through the primary piping toward the external overhead conservator tank. Tracking these specific chemical byproducts provides the earliest possible warning system. It allows engineers to catch impending failures before they cause irreversible damage. Engineers install a Buchholz relay, a mechanical gas trap in the upward piping. For minor faults, the generated gas slowly rises and accumulates at the top of the housing, displacing the oil. You can see the fluid level dropping against the graduated scale. Inside the chamber sits an upper float mechanism. As the trapped gas displaces the oil, the fluid level drops, and gravity physically pulls this upper float downward. When the float descends far enough, it closes a magnetic switch. This triggers an early warning alarm in the control room, alerting operators without actively disconnecting the transformer's power supply. This design also acts as a physical safety check for the oil itself. If a structural breach in the tank causes a slow oil leak, the fluid level in the relay drops, triggering this exact same float alarm. This upper float alarm circuit buys maintenance engineers critical time. It gives them a window to investigate and isolate the issue before the equipment completely fails electrically. But not all failures are slow. When a massive internal electrical arc occurs, the resulting chemical reaction is explosive. The sudden electrical arc causes rapid, violent gas expansion inside the tank. This creates a high-velocity physical wave of oil that surges aggressively up the pipe toward the conservator. In this schematic of the Buchholz relay, the rushing wall of oil strikes a lower flap. The force pushes the flap down, closing a trip circuit. This signals the main circuit breakers to open, isolating the transformer before internal pressure causes a catastrophic explosion. Once safely offline, diagnostics begin. Engineers use the petcock valves on top of the relay to extract trapped gas. Visual checks reveal the fault: whitish for paper arcing, yellowish for wood degradation, grayish for core breakdown, and black for severe free arcing. The elegant dual float mechanics of the Buchholz relay perfectly translate invisible chemical deterioration into direct, actionable mechanical data. However, the Buchholz relay has one major limitation. Because it only detects internal chemistry, it is completely useless against massive external grid faults. To guard against a severe external short circuit, engineers utilize IDMT overcurrent protection. This relies on current transformers mounted directly on these high-voltage bushings. The engineering challenge here is calculating the exact primary pickup current. This threshold must be high enough to allow normal operational surges, but low enough to trip the circuit the moment a real fault occurs. The calculation starts by finding the full load current. You divide the rated power by the square root of 3 times its voltage. For a 100 kVA transformer at 11 kilovolts, the full load current is 5.25 amps. Next, engineers factor in a safety margin to prevent nuisance tripping during harmless inrush currents. Multiplying the 5.25 amps by a 135% safety margin gives us a primary pickup current threshold of 7.09 amps. We then translate this primary current into a safe secondary current using the physical ratio of the current transformer. Applying a standard 100 to 5 amp ratio yields 0.355 amps, the physical plug setting on the relay. This strict mathematical threshold ensures the transformer ignores temporary, harmless spikes in demand, but acts instantly to isolate the hardware from massive external short circuits. This matrix compares the operational envelopes of both systems. The Buchholz relay offers high sensitivity for internal faults, while the overcurrent relay offers broad, system-wide protection with low sensitivity to internal issues. Because the overcurrent relay requires that 150% safety margin, there is a massive gap in its defense. It is mathematically blind to the low-level, smoldering internal arcs that don't immediately spike the current. Conversely, the Buchholz relay is perfectly tuned to catch that internal chemical decay, but it is physically disconnected from the electrical grid. It cannot detect a massive short circuit occurring outside the tank.
By overlaying these two highly specialized systems, engineers eliminate both blind spots, creating a complete, overlapping envelope of protection. Looking at this GE Transfix gas analyzer mounted on a modern unit, we can see the next evolution of this concept. Today's grid architecture supplements physical relays with continuous, online dissolved gas analysis. These advanced sensors continuously sample the oil, digitally tracking the exact same chemical signatures that the mechanical Buchholz trap catches manually. Securing the backbone of the power grid requires translating the invisible, microscopic chemistry of failure into these precise mechanical traps and mathematical defenses.